Welcome everyone to this talk for the 2025 Flight Software Workshop. My name is Skeggs. I'm a lead flight software engineer here at the NASA Jet Propulsion Laboratory, and I'm excited to talk to you today about an interesting challenge we encountered developing flight software for a particular microcontroller and the solution that we settled on for that challenge. You may be familiar with the Mars Sample Return campaign, which seeks to bring back rock samples from the surface of Mars here to laboratories on Earth so we can examine them in more detail. You may also be familiar with the fact that JPL proposed a new design for the Sample Retrieval lander spacecraft this past fall. There's a lot I won't go into about the new design, but as part of it, we decided we needed to move away from some heritage devices known as remote engineering units and replace them with a set of new devices that we're calling remote engineering and power regulation assemblies. Now, there's a lot of things that these devices do, but one of the really important ones is that they provide a bridge between the 1553 bus on our spacecraft and a bus known as the Remote Serial Bus, or RSB. RSB is where we've attached our power switch slices. And so if a compute element needs to control a power switch on our spacecraft, it needs to send that command through an REU to a PSS to control that particular switch. And to get telemetry about the state of that power switch, that telemetry needs to come back through the remote serial bus, through the REU, through 1553, back to the compute element. This means that the REUs provide a very essential function. And traditionally, we've implemented that function in FPGA circuitry. However, for the new Reaper design, we've decided that we want to use microcontrollers to implement this and all of the other functionality that the Reapers need to have. This means that my team needs to develop flight software to replicate the same functionality we had before to bridge 1553 to RSB and other things in this new design. Now, in order to understand why we selected a microcontroller, it's important to understand the use case of the Reaper on the spacecraft. You may be familiar with the fact that we're proposing that the spacecraft will use a multi-mission radioisotope thermoelectric generator, or MMRTG, to provide the power that we use on the surface of Mars. An MMRTG that, like the one we're selecting, will produce about 100 watts continuously, which is not enough to power the spacecraft. Or at least not while it's on. Which means, like previous Mars missions, we will be putting the spacecraft to sleep for major parts of each solar cycle, and using that time to recharge the battery up to a level where we can resume activities. Now, the compute element can be off, but the Reaper on the lander stage needs to be on continuously because it's the thing that wakes up the rest of the spacecraft. What this means is each watt that we consume on the Reaper translates into 1% of the MMRTG's total energy output over the entire mission that we lose. And so we needed to select a microcontroller with really low power consumption. And to that end, we selected the Virago VA41630 microcontroller, which is a 100 MHz ARM Cortex M4 with a set of very interesting peripherals packaged with it. And we'll use this instead of any kind of traditional field programmable gate array. Now, a microcontroller is really different from an FPGA. And one of the key differences is that with a microcontroller, it's kind of take what you get. If you bake a certain peripheral, like an Ethernet controller, into a microcontroller, then you can use that peripheral from the microcontroller. But if you use a field programmable gate array, you don't need to have that particular peripheral baked into it. If your microcontroller doesn't have, for example, a remote serial bus peripheral, you're kind of out of luck. There simply isn't one. But if you have a field programmable gate array, you can build one yourself. The problem is that since RSB is a JPL-specific protocol, and nobody else uses it, the microcontroller we selected does not have an RSB peripheral. Now, this is going to start causing problems, because in fact, no microcontroller that we could possibly select will have an RSB peripheral, because again, no one else uses it. Now, that means that the Reaper, without an FPGA, can't communicate with the heritage power switch slices. We really want to build those to print so that we don't have to reopen the FPGA design. But this means we'll either have to use an FPGA on the Reaper, which we really don't want to, or reopen that design on the power switch slices, which would be awful as well. Either case, we have a lot of development, a lot of new verification and validation that needs to happen on those new FPGA designs, and that's going to really challenge the overall project schedule. So it's really important that we find another solution that would let us speak the RSB protocol from our microcontroller. Now, in order to better understand this challenge, we're going to have to better understand the remote serial bus protocol. RSB is a fairly direct translation of 1553. It's a shared medium 1 megabaud RS485 multi-drop protocol with fairly stringent timing requirements. About 100 nanoseconds of jitter on each bit time, and at most 1,000 parts per million clock drift over the course of each message. It's also split into 3 separate buses: a shared medium command bus, a shared medium telemetry address bus, both of which are fanned out from the REU to the client devices, and a shared medium telemetry data bus that fans back in to the REU. So since this is RS485, the obvious solution is just use a UART peripheral. RS485 generally is compatible with industry standard UART peripherals, and we have one on the Virago microcontroller. Even though UART is normally only 8 data bits long, the Virago UART supports anywhere from 5 to 9 data bits in each word, along with configurable parity and stop bits. Unfortunately, RSB command words are 16 bits long, RSB telemetry address words are 13 bits long, and RSB telemetry data words are also 16 bits long. This is very convenient when you're building an FPGA because you have 16 data bits coming in off the 1553 bus, and you have 16 data bits going out over RSB. Unfortunately, this means that the RSB protocol is not compatible with any standard UART peripheral. The UART peripheral would necessarily misunderstand words it receives, and it would be unable to transmit in the required format. FPGAs are really nice because the world is your oyster. You can implement practically any protocol you can imagine. You want a 16-bit RS485 protocol? You have it. The problem is, when you no longer want an FPGA to speak the other end of your protocol, your world is no longer your oyster. Now you have to find some way to implement this unusual protocol on, for example, a standard microcontroller. So we can't use a UART peripheral to speak RSB. Another option we could consider would be to directly generate the output waveform and sample the input waveform in software from the GPIO pins. This seems like a decent idea on the surface, but it gets pretty complicated. Notably, it means we're going to need to produce a new bit on the output pin exactly once per microsecond. If we delay by more than 100 nanoseconds, or we're early by more than 100 nanoseconds, the waveform will be invalid, and the command received on the other end will be incorrect. Given how essential the power switch slices are to our system, it is not acceptable for us to corrupt the commands that we're sending. And receiving is difficult as well. Because it's such an essential system, the telemetry always has to be perfectly intact. But while sampling our input at the same time as our output once per microsecond would work great if we happen to be aligned with the data signal, that's not guaranteed. The UART can start the start bit at any time during the microsecond, and we have to then align to that for receiving each data bit. If we happen to get unlucky and be aligned by chance to the 200 nanosecond transition period, we would receive junk data, and the telemetry would be bunk. So we could either try to oversample at least 2.5 times every microsecond, or we would have to independently schedule inputs and outputs within each microsecond. The problem here is that the Virago VA41630 microcontroller runs at 100 MHz, or after derating, 80 MHz. That means we only have 80 CPU cycles every microsecond available to us for all uses. On an ARM Cortex-M4 microcontroller, it can take up to 12 cycles to enter and interrupt service routine, and up to 12 cycles to exit an ISR. If the microcontroller takes 2 interrupts every microsecond, we could be spending 48 of those 80 CPU cycles on interrupt, entry, and exit alone. No jumps, no data loading, no data retrieving, not even communicating with the GPIO peripheral. If it is even possible to fit in those remaining 32 CPU cycles all of the functionality that we need for RSB, it will consume the whole CPU. And RSB is only one of dozens of behaviors that we need to implement on the Reaper. We cannot dedicate the entire microcontroller to servicing the RSB interface. So we're going to have to find another solution. A third solution that we could consider would be to use the DMA engines in the Virago to drive those GPIO pins. After all, if the problem we were facing was that we were using too much of the CPU, then maybe offloading this functionality off of the CPU would solve our problem. Now, at first glance, this seems like a good idea. We can prepare a buffer in SRAM that contains all the bits we want to generate on our command and telemetry address pins, and they can be DMA'd once every microsecond based on an input from a timer peripheral, and they can flow across the advanced high performance bus, flow across the advanced peripheral bus, and get written to that GPIO peripheral. And for the data we receive back, again, through the GPIO peripheral, through the advanced peripheral bus, through the advanced high performance bus, back to the DMA engine. And we can store that in SRAM. And we could then be preparing our buffers beforehand from the software, but not need to be interacting in the moment with the GPIO peripherals. And this seems like it would work pretty well. The problem that we end up facing is that the advanced high-performance bus is configured in a way that doesn't allow this to work reliably. On an ARM bus matrix, the manufacturer of the chip that's using the ARM IP can decide how they want to configure the different priorities for the different ports. So we have a master port for the Cortex-M4. We have a master port for the DMA engine. And we have a subordinate port for the advanced peripheral bus, particularly the advanced peripheral bus that drives this GPIO peripheral. And the issue is, if both the Cortex-M4 and the DMA engine simultaneously try to perform a read or a write to anything on that advanced peripheral bus, one of them will win. And it's always going to be the Cortex-M4. Which means we could be delayed for a small number of cycles if the Cortex-M4 is doing something like, for example, efficiently copying 16 bytes from some software buffer into a FIFO for one of the other peripherals on the APB. Because our timing constraints are so stringent, we have at most plus or minus 100 nanoseconds. That means we only have a small number of CPU cycles. After we consider crystal oscillator error, we're down to plus or minus 4 CPU cycles when running at 80 megahertz. It would be trivial for a big copy from the CPU to overrule that and prevent the DMA engine from running on time. That either results in a malformed output or a misinterpreted input, which could be mission-ending if it happened at the wrong time. So we could try to rule this out by precisely analyzing what the Cortex-M4 is going to do over the execution of our software. But that requires detailed machine code analysis to understand the exact timings of different reads and writes. That is not feasible for us. So unfortunately, we're going to have to declare that the DMA engine solution also does not work. A fourth solution could be to try to use an SPI port. This doesn't sound very promising on its face because SPI is really different from UART. UART is self-clocked, right? When an endpoint sends data, it has agreed on the data rate with the other end, and so the other end just extracts the phase from the start bit and then clocks out at the known rate. And SPI, by contrast, has a main endpoint that provides a clock that the subordinate endpoint then has to follow. And the other end of our communications protocol doesn't give us a clock line. But what if we just didn't connect the serial clock or the chip select? We would have a MISO pin, which is an input. It's a lot like a receive. And we would have a MOSI pin, which is an output, and it's a lot like a transmit. And if our SPI peripheral were to be producing a clock at exactly 1 megahertz, which we could configure it to do, at least on this microcontroller, it would produce a signal that looks an awful lot like a UART, at least on an electrical level. And that signal wouldn't have the start bit, or the stop bit, or the parity bit, but we could add them in software. We could take a, for example, 16-bit UART word, or RSB word, with a start bit, a parity bit, and 2 stop bits. And we could encode that into 2 10-bit SPI words. SPI peripherals are very flexible, and ours allows us to select a 10-bit word. And so if we shift out 2 10-bit words, one after another at 1 megahertz, we could exactly mimic the waveform that we would expect to have for an RSB command. And similarly, when we're receiving RSB data, we could take the same input and go back the other way. If SPI can be synchronized somehow, then if we would receive once every microsecond, and we would have to then decode and validate the start bit and parity bit and stop bits. But the data bits would all be there. And to align our phase, well, we can't use an SPI port in main mode, but we could use one in subordinate mode. Now, to use it in subordinate mode, we have to have a main mode peripheral that we're connecting to. Or we could just have a 1 megahertz timer that we could shift the phase of. And the timer peripherals on the Virago let us do that. We could generate a 1 megahertz signal from that timer, goes out on the pin, comes back in on the serial clock pin, and we could align the phase based on when we detect that input bit, that start bit. And then we would be clocking in halfway through, exactly in the middle, of each bit we receive over RSB. And we would receive a coherent word. Again, we got to decode the framing in software, but it would be valid. And so this would let us pretend to have a 13 or 16-bit UART, even though there isn't one baked into our microcontroller, by using an SPI peripheral. And to be even clearer about this, and to make this even a better solution, we can use the cascade modes on these timers to control each other, and therefore stop and start that 1 megahertz timer at the right times to produce the outputs and receive the inputs. So for example, for you having an SPI peripheral produce telemetry addresses and receive telemetry data, we could use this configuration I'm showing here. One timer to generate the 1 megahertz clock, one timer to tell it when it should generate that clock, so it's only when there's a word going out or a word coming in, and a timer to detect the start bit, make sure it's still running after half a microsecond so it's not just a glitch, and start that clock to receive the next word. So, in theory, this would really work. I've described 4 different solutions to this challenge. 3 of them didn't work, some for fairly subtle reasons. This flight software testbed demonstrates the 4th solution. This is a Virago VA41620 microcontroller development kit. it's running a software that implements the fourth solution I've described in this presentation. It's communicating over the remote serial bus protocol using these single-ended differential interface boards to this PSS in the bag up here, which is a prototype built to print from the same blueprints that we will actually be using for the Mars sample retrieval lander mission. So we can control the power switches on that PSS over RSB and get telemetry back. That's a pretty good indication that we've implemented a solution that really works. This is a simulated load attached to power switch number 5. It's a big resistor. Across it, we currently have 0 volts because the power switch is disabled. But if we command it to be enabled over the RSB protocol, we can see we now have 32 volts. And on the screen, you can see the telemetry coming back through the microcontroller, which indicates that power switch 5 is being reported as enabled. If we disable it over RSB, the telemetry changes and the switch is actually off. Now, if, for example, we turn on the power switch but the interface board is off, then we can't receive telemetry. But if we turn it back on, then we can receive telemetry and it's still on. The power switch was on that whole time. Now, if we were to turn off the whole power switch slice, now the power switch is off because there's no power going to it, and it remains off when we reboot the power switch slice. But now the telemetry coming back indicates that the power switch is off, even though the flight software thought, because of its last command, the last command it sent, that the power switch was enabled. So this is a demonstration that the solution I've described in this presentation really does work with real heritage hardware. We started this presentation with this realization that no commercial microcontroller is going to ever have an RSB peripheral, which was a huge problem. It threw into question our whole schedule. How would we be able to develop the new FPGAs in time? How would we verify them in time? All kinds of extra steps and worries and problems. But because we're able to emulate RSB using the SPI peripheral and the timer peripheral already present in the VA41630 microcontroller, we actually can achieve that schedule that we were concerned about at the beginning. It's true that microcontroller peripherals are often designed for very specific purposes, and they're not designed to be repurposed in other ways. But it is often possible to find those other ways and to solve challenges that otherwise would be very difficult to solve. So this was not something I did entirely myself. The Reaper project as a whole has so many engineers and other people working on this. A special shout out to our testbed engineers, Ton and Ron and Luis and Demi. They really made this possible, and I'm very happy for all their support. If not for them, that demonstration I showed you I'd still be assembling that demonstration today, probably. And all these other people without whom we would not be where we are today. I haven't talked about a lot of the details of the Reaper, but this is an extraordinarily exciting project, a very exciting piece of flight software to build, and I would be very happy to answer questions to the extent that I can if you would ask me online. So, thank you very much, and I hope you have a wonderful rest of your day.